Okay. All right, so you have a couple things to mop up here for carboxylic acid derivatives. And then we'll start talking about the last chapter, which is enolates, which is what we'll do tomorrow. Alex?
Are we still going to be learning stuff until Wednesday?
We'll be learning stuff, hopefully, for the rest of our lives. But we will be learning organic chemistry through tomorrow. And then Wednesday I have some review, and actually, even tomorrow, there's some review. So if you look in Canvas, I put the chapters for carboxylic acid derivatives and for enolates. I put the ACS study guide questions on there. So we may be doing some of those tomorrow, tomorrow as well as, and then on Wednesday I can answer any questions. There's review problems. There's a set of questions from Organic 1. There's a set from Organic 2. And so we can do those as well on Wednesday. So Wednesday will be just like a review day. So I may say try some of these problems, and as you do them, you can do them in groups, and then I'll walk around, and if there's something that stumps everybody, then we can go back and remember it.
And then for the final, I'm assuming that we didn't catch up to what we need to do for the final. So if there's stuff on the
Oh no, we'll be caught up.
Oh, we will.
If there's stuff, so it's an ACS final, but what I do is I use it as a final first and an assessment tool second. So the reason that people give ACS final exams in almost all the organic courses in the country is that they can use it as an assessment tool. So I can use it from year to year to see how people at the class average is, and I can also use it to compare against national averages and see how people do there. Now there's kind of a mismatch between some of the topics we talk about and what's emphasized on that exam. For instance, that the ACS exam tends to overemphasize carbonyl chemistry that we get to in the last portion of the semester. So that tends to lower the scores. But I know pretty much where people, get, what scores people get. And I also put a break on it, just totally tanking your average, so that if you're kind of on a line, you always want to do the best you can. Around here, the thing that annoys me the most is when I hear students like, it doesn't matter, I'm not going to study for it, doesn't matter. It matters. And if you don't study for it because it doesn't matter, it will matter more. Much more. So it counts, but like if you're going in at whatever grade, will it cost you, a full grade? Probably not. But if you're on a line, you could go down a third of a grade. And that's usually as far as I let it go. But it's used as a final exam first. So when I skim through the exam, if there's something that we haven't talked about, then I just basically eliminate that question. So that way there's no question of you looking at it going, I don't know if I remember this, or I don't, then okay, you're not answering that question. But that's why we give the ACS finalists, so that we can do assessments, because everybody's required to do assessments to see where, this way I can say, oh, they were a little bit below national average, which is pretty much how the class goes. I've never taught summer, so I have no idea. I know looking at the data in the past, it's usually about average. But you want to do the best you can. And I know this week, it's kind of a truncated week, and there's a lot of stuff going on if you're in lab and lecture. So, so that's the That's the reason we give the final exam, and that's my philosophy is it's a final exam first, so am I going to just put your raw score in? No, I'm not just going to put your raw score in. I usually scale it to whatever I choose to scale it to. Sometimes it's a high score. Sometimes it's a little bit below that. But then when I have the final average, I'll go back and look through that. So where you're at now is close to where you'll be at the end of this. But you still got to study. So I don't leave the impression that it's like, oh, it doesn't matter, because as I said, it matters. You want to do the best you can. But these are always hard tests. So the average is probably between 55 and 60%. Is usually the average. But if I write a really good multiple choice test, the average is probably between 65 and 70. So, and we'll do some multiple choice problems tomorrow and on Wednesday so that you kind of get a feel for them. But if you want, there are ACS study guides for organic in the library on 2-hour reserve that you can get your hands on. And if you have somebody who already has purchased one, I don't think I have. I think what I have in my office is just the ones that came back from the library, which look like somebody ran over them with a lawnmower. And it's just paper everywhere. So it's not even a book anymore. So, but that's how I approach the final. So, but there's only one topic that I can think of right now that we haven't talked about that may be on there, and we may talk about that, and that's aromaticity, like how you specifically determine if something's aromatic. All right, so that's where we're at. And there's different versions of the ACS final, so if you end up taking this again at your school, it may be a different version. And sometimes there are easier versions and harder versions. It depends. And let me just a couple things mop up here. You got a link for the course. You got a link for the course evaluations, which are not controlled by me. So you could. I think it's open till Friday, which is a dangerous thing to do. To leave course evaluations open after the final exam when everybody's like ready to be not positive. But the course evaluations are there. I did not do one last semester because quite honestly I forgot about it. So you can comment on both semesters if you would like, if you were in both semesters. And those are handled like they may be handled at your school. Which is, you're not going to get me fired because I have tenure. You're not going to get me a bonus either. So either way. But I do take a look at it. I do take a look at them, and as I have all 2 weeks to plan for the fall, if I'm going to make changes, I usually look and see like what people thought was effective. Not necessarily what you liked, but what you thought was effective. Like I think in the fall, we're going to be breaking up into groups more than we did this semester. And I'm going to go back to more of the flip lecture, but you can give me your comments on that. And so those are due on Friday. I assess you by a grade, so this is your opportunity to formally assess me. RateMyProfessor.com is not a formal assessment. And there is no RateMyStudents.com, although I've threatened to get together with people to make that. And that would just get people fired. Right? Although they have removed the chili peppers from Rate My Professor. You may be of an era where the chili peppers never existed. What is a chili pepper? What do you think it represents? Exactly.
Oh.
So it may be that they eliminated that since it's been around. But that used to be an issue. That would get people fired if they did that. RateMyStudent.com. I have a whole rant on it, but it really doesn't do any good anymore. Okay, so that's kind of. So you want to study for the final. Like I said, I will eliminate any questions that I don't think you can answer. And for the most part, there's one answer for all the questions, but if there's a question that maybe has more than one answer I think you could get from what you've learned, I will code that so that you would get either half credit or full credit. So sometimes that happens. And if you find a copy of an ACS exam online, you better download it because they scan those things every day. Because you're not, I mean, you can get in big trouble if you put it electronically. And I've had students try and steal them by like trying to intercept them in the mailroom when they've sent them to me. That was a whole crisis. Cameron?
So for the final, or just like a second class, what's like the last chapter?
26.
26. Okay.
Which is what we're going to do tomorrow. Yeah, there's only 2 chapters that you can't see. One on polymers and one on biochemistry. And if you go on and take biochemistry, you're going to learn far more than what's in that chapter, like amides and sugars and proteins and that kind of stuff. I will release those so that you can have them, because you will have access to this book online as long as the company exists. So if you want to go back and look at something, you can certainly do that in Top Hat. That's the purpose of this book. If you want a hard copy of an organic book, you can get any organic book you want because they're all the same. But you'll have an electronic version of this for forever. Some publishers only give you like 4 years or 2 years. This company said they'll give it to you forever. And if they go out of business, but they're not going to go out of business. And they have Ohio State and other places that they're selling to. Not chemistry. Ohio State chemistry doesn't use that. They use something else. Because I know people down there. And they haven't made a switch yet. But other places, that's one. So whatever you paid, it's less than the $300 you're going to pay for a brand new book. But you'll have access to it. And you don't have to do anything. You'll have access to it. So that's kind of how it works. Okay, anything else? So tomorrow we will be doing, but I'll mix in some multiple choice problems on the enolates, on the carboxylic acid derivatives, and then on Wednesday, like I said, we can do more. We can do as much review if you want to. You can work on problems, or you can ask questions. Like how do you do RS or something like that. But it's going to be, the exam's comprehensive over the entire year. So it may be a while since you've taken first semester. I don't know what to do about that. But like I said, I put the brakes on it, completely destroying your grade. Which is not always the case. Okay. So remember we worked our way to put you back in the organic mindset here. We listed our carboxylic acid and our derivatives in this order from top to bottom, with the bottom being the least reactive and the top being the most reactive. So acid chlorides are the most reactive, then anhydrides. Carboxylic acid is not really a derivative, but I put it there because what I'm doing is I'm looking at each one of these reactions in terms of this group that I just put a square around being the leaving group. And so I'm basically going chloride, best leaving group, anhydride next best, hydroxide next best, OR next best, NH, NR, the N group, least. Best leaving group, or worst leaving group. So, also, in the carboxylic acid derivatives are nitriles, and the reason nitriles are there is because when you hydrolyze those with H plus H2O, you will get a carboxylic acid. So, those are our derivatives. I don't know where to put nitrile on that chart because, quite honestly, a C triple bond N, what kind of leaving group is it? It never leaves by itself. It always gets converted to something else. So we had basically worked our way through all but the last two in terms of reactions, in terms of adding Grignards or organolithiums, or reducing it with lithium aluminum hydride, or our new lithium tertiary aluminum hydride. And then also the question is Grignard versus cuprate versus Gilman reagent. So we have two that are kind of left here to go over a couple of things quick. So everything above can be turned into something below. So when you get to amide, you're at the bottom of the list. So everything above it can be turned into an amide, but what can an amide be turned into? Carboxylic acid. And so if we hydrolyze an amide, if we take our amide and we treat it with H plus H2O, we're going to end up forming the carboxylic acid, and then since it's in acidic conditions, we're going to end up protonating nitrogen after it leaves so that it basically will become an ammonium. So that's all we can do with the amide as far as conversion. It can only be converted to a carboxylic acid. And the mechanism for this is kind of the same mechanism that we've done with others. But with that mechanism, what I want to do is I want to talk about one thing I haven't in terms of esters and amides. So, what's the first step in this mechanism? If I would have given this to you an hour and 45 minutes ago, what would you have done as the first step? Protonate the carbonyl oxygen. We agree? Now, in general, which atom's better as a base? Oxygen or nitrogen? So I don't know, so I have to look at the periodic table. So which one's more basic, nitrogen or oxygen? Nitrogen. So should I protonate the nitrogen in the amide then? Rhetorical question. I think most of the questions are going to be rhetorical today. Not so tomorrow. No. I'm not going to protonate the nitrogen in the amide. And if this was an ester, I'm not going to protonate that oxygen that's part of that's not the carbonyl. And you may say, well, why not? Nitrogen's more basic. Why shouldn't I protonate it? And the answer is because you don't, but why? Well, if I take an ester or an amide, I can draw the following resonance structure. I can take this pair of electrons, move it here, and move that pair of electrons to the oxygen. So I can draw this. With a plus charge. Okay, so I can draw that resonance structure either for an amide, or if I started with an ester, it would look like this. So that resonance structure, is it stable? Is this resonance structure stable, yes or no? Take a guess. What? Good guess. No, it's not stable. Should be more than a guess, though, shouldn't it? At this point, it should be. Why is that not stable? What are its issues? There's a positive charge on the nitrogen. That's an issue. What else is an issue? It's got a positive and a negative charge. It's got two charges. So this thing has two issues. It's positive and a negative, two charges, and the nitrogen gets a positive charge. So it's not stable. However, what would be the resonance hybrid of these two? Because even though it's not very stable, it is still kind of contributing. So if I was to write the resonance hybrid for this, the oxygen would be slightly negative and the nitrogen would be slightly positive. So this would be the resonance hybrid. And over here, the resonance hybrid for the ester would look exactly the same. So that would be the resonance hybrid for the ester. Now, what is my point? My point is that if you're an H+, who are you adding to? Are you adding to the thing that's delta plus? No. So you're going to add to the carbonyl oxygen, which is delta minus. So when we add acid to amides and esters, we never add the H+ to the nitrogen or to this oxygen, because in the resonance hybrid they are slightly positive. Now, it's not a big positive charge, but they are still slightly positive. And so that's not where the H+ is going to go. The H+ is always going to go on the carbon. So for amides, despite the fact that nitrogen is a better base atomically, in an amide you always still protonate the carbonyl oxygen. Okay, so that's the first step in the hydrolysis mechanism. And then you would go through and basically follow the steps. Eventually you're going to protonate the nitrogen once it's no longer an amide, and that N+ group is going to leave to form the carboxylic acid. I suppose I could make that a take-home quiz problem, but I won't at this point. So that's hydrolysis of amides. That's all I can do. Now, what about taking the amide and treating it with hydrides or with Grignards, or hell, even with cuprates. What do I do there? And so what I can say is, here's my amide. So I'm going to treat this with lithium aluminum hydride. And what am I going to get? Well, what happened when I treated an ester with lithium aluminum hydride? What did I get? Did we have to do that? On the test, did we have to do that? We had the option of doing lithium aluminum triterpenoxy aluminum hydride. That's what we should have gotten. Or did get. Splits. So when you react an ester, it splits. Why does it split? Because the OR group can be made to leave. I'm going to contrast this with what happens with amides. Nitrogen is a worse leaving group than OR. So when you treat an amide with lithium aluminum hydride, you are not going to split. Instead, what you're going to do is you're just going to reverse, or just going to turn this carbon into a CH2. So you're going to get an amine. But you're not going to split the molecule apart. And the easiest way to remember that is because nitrogen is not going to leave. So when we reduce an amide, we get an amine. But when we reduce an ester, it splits apart. So we get two alcohols. Okay, what about what about a Grignard? I'm going to add a Grignard to an amide. What's my first step?
Now.
Actually, in this case, there's going to be only one Grignard. Yep, it just attacks. Then what happens?
Aishwarya. Brandon.
We keep going until we hit somebody that's here.
Eleanor.
What tries to happen next? I got an O minus. It tries to become what first? Tries to reform the carbonyl. So the O minus tries to reform the carbonyl. Is it going to be successful? No, why not? Well, it would have 5 because something's got to leave. Is methyl leaving? if you take nothing else from this class, methyl ain't leaving. Is nitrogen leaving? If I could protonate it, it would, but guess what? No acid because I'm in basic conditions. Okay? So I'm stuck. So what does it do? It waits to be protonated. So it waits, I dump in some acid, and now I make an OH. Now this species is the nitrogen equivalent of a hemi like acetal. This is called a hemi-aminal. That's the nitrogen equivalent. And just like a hemiacetal, sorry. Yeah, it's still a hemiaminal. So, in this case, I would have a ketal because it came from a ketone. Or it's got two R groups here, sorry. So this one would have come from a ketone. But this hemiaminal is not stable just like a hemiketal would be not stable. So what happens to this in the presence of H plus and H2O? It's going to revert back all the way to a ketone. Right? I'll even take my highlighter and I'll highlight this because I think this is the third time I've done this in class where we're going to take this hemiaminal and now it's going to go ahead and it's going to form the ketone. So if you want to take an amide and make a ketone out of it, you could using Grignard. Because the Grignard's going to add one R group, you're going to make the hemiaminal, it's not stable, and so it's going to revert back to the ketone. And you probably know what's coming next. Or not. My next question would be, let's take our amide and now let's add lithium, aluminum, triterbutoxy, aluminum hydride. So now how many H minuses am I adding? 1. What's that H minus going to do? Might as well give somebody the opportunity to answer an easy question.
Aishwarya.
Okay, it should be taking her name away. There.
Greg.
What's the H minus going to do? It's going to attack the carbonyl. What's going to happen next?
Max.
What's going to try and happen next? It's going to try and reform the carbonyl. Is it going to be successful? No. So what's going to happen? Wait to be protonated. Alright, so I added my H minus. What did I just now make? I now just made a
Calais.
I don't know, what do your notes say? So we make a hemiaminal. Is the hemiaminal stable?
Hannah. Cameron.
No. So what's going to happen? It's going to convert it all the way back to an close aldehyde, right? I'll highlight there. So it's just going to take it all the way back to an aldehyde. So if you want to take an amide and make a ketone out of it, use a Grignard. If you want to take an amide and make an aldehyde out of it, you can use the lithium aluminum triterpenoxy hydride and add 1H minus. You're going to form the hemiaminal, which is unstable in acidic conditions, and so it's going to revert itself all the way back down to the aldehyde. So, and at this point, if you're like, we get it. It's kind of the same steps as what I guess what I asked you to do on the exam. Then good, because that's it. That's all it is. So it all depends on this group, whether it's a good leaving group or not, and we're at the bottom of the list. So at the bottom of the list, nothing's leaving. The nitrogen's not leaving. So, we have one group left, the nitriles. Did I hear boring? Tedious? I'll agree to either one of those words. It is, because it's the same thing over and over and over again. What do you want to add to this? Let's start with something easy. Let's add 1 H minus with lithium aluminum hydride. What's the H minus going to do?
Calate.
Okay, then this pair of electrons is going to move to the nitrogen. So first of all, carbon-nitrogen triple bond is going to react the same way as a carbon-oxygen double bond. Except it's going to leave then a C with the double bond with the nitrogen with the minus charge, and now I've added my H to it. Now, since I added 1 H minus, I'm done. So now what's going to happen? I'm just going to go ahead and add acid and water. And what am I going to get? I'm going to get that. And I forget, what is that called? That's what you said first. And then you said enamine when it starts with I. So it's an imine. Are imines stable? This is why I have to keep doing this.
Greg.
Stable or not? No. So what's going to happen to it? What? It's going to become an aldehyde. So what happens when it gets treated with acid and water? It gets converted to an aldehyde. Where did it come from? An aldehyde plus ammonia. And you may say, well, why are you just assuming that acid and water? Well, because I added acid and water in this step, it's still there. So it's going to react with that acid and water, it's going to form the aldehyde. All right, I'm going to add lithium aluminum hydride, no tertiary to modify it. Lithium aluminum hydride is a source of H minus how many? Up to 4. First H minus is going to do what? Attack the carbon. I'm now going to end up with this. Except the problem here is that my AlH4 minus has now lost an H minus, so now it's going to be a sort of a counter ion with the AlH3, which I'm going to now write as AlH2 with another H on it. So what's going to happen now? Another H minus is going to come in and attack the carbonyl, and this pair of electrons is going to go to the nitrogen, but now that's going to be counteracted by the aluminum H2 with the plus charge. So I'm going to end up with something like this. That's good. You have a sense of deja vu. We did this with actually the esters and the carboxylic acids. So yes, it's a similar mechanism, but here's the difference. What eventually the aluminum was able to do was to grab the oxygen and pull it away, because an aluminum-oxygen bond is so strong. Aluminum-nitrogen is not as strong, and so the aluminum is not going to pull the nitrogen away. Instead, what's going to happen is we're just going to hang out until we add H plus H2O, and I'm going to end up now, let's see, I added I formed my second, so then I'm going to end up with a CH2 now with an NH2. So I'm going to reduce my amide, or my nitrile is going to be reduced all the way down to a primary amide. So the aluminum, because the aluminum-oxygen bond is so strong, aluminum can take an oxygen away. But in this case, aluminum-nitrogen isn't, so it's just going to kind of be bonded to it until the H plus H2O comes in. And then the N minus is going to become an amine. Let's see, what else do we have to do with nitriles? We did Grignards, right? No, we didn't do Grignards. Alright, humor me. Oops. I'm going to go ahead and add my Grignard. What's going to happen? The R minus is going to attack the carbon, and the pair of electrons is going to move there. So now I just added my R group. What happens next? Nothing. The only reason I can add a second H minus is because the aluminum is able to stabilize the N minus. I can't form an N2 minus. That's too much. So it just hangs out, waits to be reacted with H plus H2O, and what do I end up with? I end up with this.
Megan.
Here's your question. Unless you have a question you'd like to self-ask. My first question, what is that? It's an imine. Imines are imines regardless of whether they're aldehydes or ketones. So I made the imine with the aldehyde before, now I made the imine with ketone. So I made an imine. Is our imine stable? Not in acid and water, so what's this going to convert back to? The ketone. And that's it. That's imines. Or nitrile reactions. Right? Nothing exciting. It's the same thing over and over and over and over again. Now, now we're into multiple choice mode. Right? We have to move into multiple choice mode for the final exam. Does that change how you study? Now, if you were my freshman cohort from 2 years ago of advisees, when I asked them, trying to focus on some study skills in their first 2-3 weeks of class, and said to them, if you have a quiz on Friday, how are you going to prepare for it? And they promptly said, what kind of quiz is it? And I said, what does that have to do with anything? They said, well, if it's multiple choice, then I don't have to study for it because I'll just guess. This is the difference between freshmen and non-freshmen, right? If you are taking that approach into the final exam, you will fail. And it will not even be, it will be a spectacular fail. You will get less than the 25% that you could guess just simply by guessing. And nobody's going to do that. But when we go into sort of multiple choice mode, what are we going to think about? Well, what? Eliminate what? No, it could get you could give me an answer to it. Just depends on what kind of answer it is. No, that's a perfectly reasonable strategy, right? To eliminate the incorrect answers. Now, I'm going to say that a lot of these problems we could do if we just know the names and the structures we're going to get, because they're inconsequential, right? If I'm taking a triple bond and I'm adding hydrogen and palladium to it, and I know I'm going to reduce it all the way down to an alkane, there's probably going to be at least one answer there that I can eliminate. So worst case scenario, I'm guessing 1 out of 3. I don't like those odds personally, but it's still 1 out of 3. If you can get it down to 1 out of 2, again, still not great odds, 50-50. But so when you go into sort of thinking about the possible answers being there, my suggestion is write the product out like you would normally do, and then see if it's there. sometimes if it's Markovnikov, anti-Markovnikov, you're going to see them both, but, you know, at least you're doing that. So that's one of the reasons, or that's one of the suggestions, is if you're looking at answering multiple choice, write the problem out. Write the answer out, and then see if it's there. I have, one of these days I've tried this before, where people say, which is more rigorous, writing the answer out or multiple choice? Right, that's a good academic question. Which is more rigorous in organic chemistry? Because a lot of people just give multiple choice exams during the semester. I only give two finals, or multiple choice. Sometimes a fourth exam, but once you write a good multiple choice question, then I put it on the web and it's out there for everybody. So I would give people front of the quiz where they would write out the answers, and then they turn it over and do the multiple choice. As usually some people got points, some people got, you know, it was give and take. So you ended up about where you were. Very few people did super better. Very few people did super worse. Usually they cancel each other out. Usually it was like you write a name, you forget the E or Z, and then you turn it over, it's like, oh, there's the E or Z. So the approach would be to, as you're studying this, do it exactly the same way. Use exactly the same methodology that's been hopefully working for you. But there are plenty of multiple choice type problems that are reviewed on, you know, for the 2 ACS in today's folder, in tomorrow's folder, and then in the Wednesday folder, there's multiple choice over both first semester and second semester. So as you're going through those, maybe write questions, and we can deal with those on Wednesday. We can deal with those tomorrow too. Okay. But tomorrow what we're going to do is we're going to do chapter 26. So we're going to do enolate chemistry, which is going to be somewhat more tedious because it's the same thing over and over again. But the people who write ACS finals are fixated on enolate chemistry. So some of the problems we'll be doing tomorrow, I will almost guarantee you'll kind of see on Thursday. So hopefully Tuesday to Thursday, not much can evaporate from here. You just have to keep it all in. And then on Friday, somebody else's problem. Okay. All right, so questions, bring them to class tomorrow. Otherwise, that's what we will do. And at the latest, I'll have your exams from today on Wednesday.